In this lesson, we're going to start to look at geometry and algebra and what math is in general and how these two have kind of come together over the years. So first it says math is, in its essence, the science of patterns. So in math, we can look at a lot of different things. Two things you've looked at so far are algebra and geometry, and what are the patterns that are always true in these two areas. Some of the questions or some of the patterns we find in geometry are congruence of triangles whenever side angle side is true. So you don't need to know every side and every angle. If you know a side, an angle, and a side of the two shapes are congruent, then basically you know those two triangles are congruent. A couple other ones you can read through: diagonal congruence in a rectangle, the relationship between the circumference of a circle and its diameter is constant, that's pi, and a central angle is twice an inscribed angle in a circle. So I just picked a couple of these different patterns we see in geometry. In algebra, whereas geometry is mostly concerned with points, lines, surfaces, solids, and higher dimensional extensions, algebra is the part of mathematics in which letters and other general symbols are used to represent numbers and quantities and formulas and equations. So in algebra, we use things like x to represent any number, and we say, well, how does it always work? So a couple of patterns we see are that if we do a squared minus b squared, one thing squared minus another thing squared, that's equal to the first thing plus the second thing multiplied by the first thing minus the second thing. So we know that is the pattern of difference of perfect squares. So here's some other patterns just represented with those variables, and that's the part of math we call algebra. So for thousands of years, going pretty far back, people did study geometry and algebra, but they were very separate. So we talked about shapes. Some people did shapes. Some people talked about how there were patterns in the numbers, and we used variables to represent them. But a really important discovery that came about was this coordinate plane, and that's when the two kind of came together. So this mathematician, René Descartes, invented the coordinate plane and the resulting field of analytic geometry. So basically now we could take shapes and we could put them on this plane and give them specific coordinates with the x, y. Points have locations represented by algebraic variables, so we started to use variables in geometry. We talked about the slope of a line, and that's an algebraic formula. The distance between 2 points, if you remember that from last year, and midpoint are also algebraic patterns. Now, it's hard to even think of it any other way now, just like it's hard to imagine the world before modern technology. So now, this coordinate plane is so much a part of math that it's hard to think about, well, what was it like before it? Now, more importantly for this course, because we're focused on algebra, once we had this coordinate plane, not only could we take geometric figures and think about them algebraically, we can take algebraic expressions and think about them as shapes. So we're going to see that on the next page. So the first algebraic expression we're going to consider is 3x plus 1. So 3x plus 1, 3 times the number plus 1, we can think of outside of anything that's a shape, but with the coordinate plane, we can also graph it. So we can graph all the outputs or the y's of 3x plus 1. So if we graph this, what shape would it make? And the answer is a line. And really what we would just start to do is plug in numbers. So let's say I plugged in a 0, right? And that would give me an output of 1. So when I start with a 0, I get a 1, and we call that the y-intercept. When I plug in a 1, right, I would get 3 times 1 plus 1 is 4. So when I start with a 1, I get a 4. When I start with a 2, I get a 7. And we can quickly see, and we know from what you've studied before, that if we kept plugging in different values, and we could plug in decimals or fractions as well, that's a little ugly, but we get a straight line. And the best I can do with my stylus is that. So the shape we see is a line. Now, different questions we can ask about this. It says, using the x-axis as a reference, what is the height of 3x plus 1 when x is 3? So if I go over here and I look where x is 3, the height up here is 2, 4, 6, 8, 10. Now, we don't really talk about it as the height, we talk about that as the y value. But really, that's what we're talking about, and height is a geometric concept. What is the height of 3x plus 1 when it crosses the y-axis? We know that is the y-intercept. Well, the height is 1. Then we can also talk about slope. That's a geometric quality that we're talking about something that is algebraic, such as 3x plus 1. So the slope we can see, if we go over 1, we have to go up 3. So change in y over change in x, the slope is 3, and we can actually see that from the algebraic expression. So the next one is kind of weird. It says if you were to create a shape between the y-axis, the x-axis, y equals 3x plus 1, so that's our line, and the line x equals 3, what would its area be? So I'm going to draw the line x equals 3. I'm going to chase that. I'm going to trace the y-axis and the x-axis, and then the function. I'm going to ask what that area is. So there's a bunch of different ways I can tackle this. I'm going to think of this actually as like a little rectangle down here. So the rectangle has an area of 3, and we can just count the boxes, or 3 times 1 is 3. And then this section here has a height of 9 and a base of 3. Now I know the area of a triangle is 1/2 base times height, so I'm going to do 1/2 3 times 9. That ends up being 13.5, so I get 3 plus 13.5 is 16.5. We're really counting these little squares, so we say that's units squared. So we can actually, another geometric concept, right, area, we can find area of these figures. So moving down the page, it says these questions about 3x plus 1 all have geometric concepts in them. These questions were not asked for thousands of years until 3x plus 1 could be viewed as a geometric figure. So when we take these algebraic expressions and we put them on graphs and we start to look at their shapes, they form families of what we call functions. So the parent function basically is like, what's the simplest thing I can make that's in that family? So for a line, we're looking at the linear family, we got a straight line. The simplest line is just y equals x. So we would say that's the parent function for lines. Its shape is a line, and we even have that in this name. And how would we tell if a function will be a line? Basically, we look for x to the first power is the highest power. Now, we could get a little more technical with that, but when we're talking about the type of functions we're talking about over the next month, that's kind of the best way to think of it. So now we're going to look at a different algebraic expression and see what shape it makes. So here we have the expression negative x squared plus 4x plus 5. So we're going to graph it on the coordinate plane to the right. And I'm just going to start the same way I did before. So I'm going to plug in a 0. I'm not going to show all of the specific ones, but I'll talk through this one. So if I plug in a 0, when I plug in 0, I get 5. Okay. And if I continue to plug in points, so if I plugged in a 1, and this is the last one I'm going to show. Okay, so if I plug this in, I have 4 plus 5 is 9, minus 1 is going to be 8. And if I plugged in a 2, and a 3, and a 4, and then just going back in each of these directions, we get here and here. And once again, not my best graphing with the stylus, but we get a different type of shape. So this shape actually has some different mathematical properties, and they knew about it outside of, it actually existed as a shape on its own before we talked about it as being a shape from a function, and that shape is a parabola. So using the x-axis as a reference, what is the height of negative x squared plus 4x plus 5 when x equals 3? So if I come over here and I go over to 3, I see that the height is 8. What is the height where it crosses the y-axis? So the height is 5 there. In the linear example on the last page, questions E and F asked about the slope and the area. So the question is, why are these questions harder to answer for the parabola? So if we try to talk about the slope of the parabola, there is actually a way to do it, which we'll talk about in a second, but we can't say the slope is 3 because the slope is always changing, and the slope is 0. The slope is 0 somewhere, and it's also 3 somewhere, but it's not always any specific number. In the same way with the area, because it's a curve, we don't have nice clean formulas like the area of a triangle or the area of a rectangle. We really can't break it up in the same way into those shapes without thinking about things differently. So basically, why are they harder? Is because it's a curve. Okay. Now, just as a side note, it says these problems, slope and area related to curve figures, frustrated mathematicians doing traditional geometry for thousands of years. So when they had these shapes, they actually knew about parabolas and something called conic sections. Circles are also a curve shape, and they were trying to find good ways to find the area of these shapes. They had ideas, but they needed the power of variables and the patterns in algebra to get control of these geometric problems. So once we started to make shapes out of algebra, we could use all the things with algebra that we do, all the manipulation of variables, and they actually found ways to tackle that area question and the slope question. The methods to tackle these two problems developed shortly after the coordinate plane, because once, it's kind of just moved things forward when we could think about algebra and geometry together, and we call these methods calculus. When they revolutionized, this is a typo. They revolutionized the way we live in every aspect of life because patterns and change are everywhere. Speed, financial matters, organism growth, disease management, mechanical processes, ocean tides, hormone fluctuations, crowd control. Human progress since the mid-1600s has involved quantifying and then harnessing these patterns. So what initially just kind of seems like a trivial math question, like what's the slope of a curved line, what's the area under a curved line, actually applies to so many areas of life. And once they figured out how to do the math with it, we were able to make a lot of progress in terms of how humans live. So kind of back to what we're talking about these parabolas, and we actually have a different name for the function. We call them quadratics. So the shape is a parabola. We'll write that in. But algebraically, we call them quadratics, or the quadratic family. So the very most simple quadratic function, the quadratic parent function, is just y equals x squared. How to tell if a function will be a parabola? Basically, x squared, or 2, is the highest power. So in our example, we had an x and we had a constant as well, if we just look up at the top of the page. Right, but if we look for the highest power, right, the highest power is x squared. In this case, it's -1 x squared.